So as I said, the first error correction technique that we discuss in this paper is based on CRC. So this is the paper that we referred to. This was a conference paper which was published in 2009. So I referred to this paper to understand how CRC can actually be used for error correction as well. So basically in computer networks today we use CRC for error detection, right? When we transmit data packets, say over a LAN or over a Wi-Fi network, the receiver does a quick CRC check and sees whether the received packet is correct or not. So it basically is used for error detection. So if it detects an error, it will send a message to the receiver to the transmitter saying that, okay, I detected a false packet, can you resend the packet? So this technique is called automatic repeat request, or the ARQ. So but here we will see that we can actually use CRC for forward error correction, which means that whenever a receiver receives a packet, it can do some computation at its end to detect whether there is an error in the packet or not, and if an error is detected, it will try to correct the error at its own end without letting the transmitter know that there was an error in the transmitted packet. So now this is the CRC based error correction. I just talked about where CRC is typically used. It is used in computer networks, it is used in hard disks, and whenever you want to do a quick detection on the error, we use the CRC. Again, I'll briefly talk about the CRC computation basics. We'll see how error detection is done using CRC, and then we'll show you an example where we are able to correct errors using this technique. So now here is an example of using CRC. These bits right here, which are mentioned in bold, these represent the message sequence. So we have the message sequence represented as GX, which is nothing but 110010. We have the generated polynomial, which is 1101. So we basically divide the message sequence, we append 3 bits at the end of it. So these 3 bits represent, these 3 bits correspond to the degree of the generated polynomial. We append these 3 bits here, and then we divide the message appended with these 3 zeros with the generated polynomial. And then we do the division. We find out the remainder. We see that the remainder here is 100. And we don't really require the quotient here because this is not required in the computation. What we actually need is the remainder right here. So the packet that we will transmit would be these 6 bits corresponding to the message, and then we will append 100 at the end of these 6 bits, and then we'll transmit. So essentially here we are transmitting 11001010. Now at the receiver, say for example the receiver received all these bits without any bit actually getting flipped due to the errors induced in the channel. Now say for example there was no error, that occurred, so we still receive 11001010, and then we again divide it by the generated polynomial at the receiver's end. So what we get as the remainder is 000, which means that the reception was error free. Now what if there was an error in the 4th bit here? Now if there was an error in the 4th bit, we would have computed the remainder, which turned out to be non-zero, right? Now this remainder says that, okay, if this remainder is non-zero, we actually get to know that yes, there is an error in the received code word, and then this code word is not what was actually transmitted. So now here comes the interesting part of error correction using CRC. It turns out that if you have a smaller space in terms of the number of errors that can occur in the data bit, there could be a one-to-one correspondence with the remainder and the message bit. So with that I mean that we can form a lookup table which can say, okay, if the remainder is 011, then the error would be in the 4th bit. So now depending on the generated polynomial, these lookup tables would change, but then since the transmitter knows what the generated polynomial is and the receiver knows what the generated polynomial is, we can have these lookup tables at the receiver. So let's quickly take a look at one of these lookup tables. So now I derived this lookup table doing some MATLAB simulations on the CRC polynomial of order 5. So which means that if the remainder is 7, it would mean that the error location is 12. So at the receiver you compute the remainder, you find the remainder to be non-zero, you know that there is an error in the received code word. What you essentially do here is, you go to the lookup table and try to do a mapping. Okay, my remainder was 8, which means that my error was at the 4th location. So then what you do is, you go to the 4th location, you flip the bits, you again calculate the remainder, and then if you get a remainder as 0, you actually know that now the data value after flipping the 8th bit is, after flipping the 4th bit is the correct data value that you require. So again here, since the order of the polynomial is 5, the maximum number of unique remainders that you can have is 2 power 5, which is 32, and then there would be one remainder which would be 0, so essentially there would be 31 possibilities of remainder possible, right? So here it limits the size of the message that you can use, because if you are correcting 1-bit errors, the size limit essentially would be a data size of 31 bits. And then this 31 bits actually includes the CRC bits as well, which is 5 here. So again, the data size that you want to use in this case would be 31 minus 5, which is 26. So if you have a data packet of size 26, then you can append 5 bits of CRC, and then you can be sure of correcting 1-bit errors in this CRC, considering the fact that you have the lookup table present at the receiver's end. Now this concept of single bit error correction can also be extended to correct the double bit errors. So now when you want to correct the double bit errors, you want to make sure that the data space that you have for the remainders, for unique remainders, should be of the order of LC2, right? So now LC2 should be less than 2 power 7 in this case when you are using a generated polynomial of size 7, because you can have LC2 number of combinations of doublets of errors that can be there in your data stream. So your error could be at the 1st location and the 3rd location, your error could be at the 7th location and the 9th location. So it turns out that there could be these many different possible number of combinations of 2-bit errors in your entire data stream. So, but the problem with double bit error correction that I saw during the simulations was that even a larger remainder space does not yield a unique remainder. So I'll come to this explanation in the next slide. So what we saw in the simulations was that we had one common remainder for these two cases, which means that if the remainder was 2, if the remainder was computed as 2 at the receiver, it meant that the error locations were 3, 11. Alternatively, it could be 10, 14 as well. So here lies the difficult part at the receiver's end. So here the receiver would have to actually try flipping bit number 3 and bit number 11 if the remainder received is 2. And then it has to again compute the CRC. It has to see whether after flipping the bit number 3 and bit number 11, CRC of 0 is generated or not. And then it will flip 10 if a 0 is generated, if the CRC checksum calculated is a 0, then it knows that okay, the error was in the 3rd location and the 11th location. So it actually knows that okay, the error was at the 3rd and the 11th location. What I just need to do is I need to flip these values and then I get the correct data. If not, then it has to go back and then flip bit number 10 and bit number 14. Right? So you see that as you move on to correct multiple bit errors, the amount of resources that is used goes up exponentially, in the sense that you have to do multiple computations at the receiver to actually get the correct data. So again, if we move on to multi-bit error correction, we can see that the amount of resources that will be required, like you'll require more computation, you'll require more memory for the lookup tables at the receiver. It goes up exponentially, right? So that is the trade-off that I'm talking about. If you want to correct more errors, you have to have more resources with you. So also let's take a quick look at some of the results on how message size would decrease, considering that there are some limited number of resources. So now this graph shows that, so we have 4 lines here. Now this is for 1-bit error correction, 2-bit, 3-bit and 4-bit error correction. So Now if you want to correct single bit errors in a data packet of size 100, then you will have to use a CRC polynomial of order 6 or 7 probably. But if you want to correct 2-bit errors using the same number of resources, you will have to use a CRC polynomial of order around about 11 or probably 12. So you see that you require a higher order polynomial for if you want to correct more number of errors in the same size of packet. So now it turns out that, as you move on to correct multiple bit errors, the amount of redundancy that you will add to the channel will increase drastically. And again, there is one big drawback in the system, which is that you first take a look at the lookup table for 1-bit error correction. If you are able to generate a remainder of 0, it's fine. If you are not, you go to the lookup table of 2-bit error correction, then 3-bit and then 4-bit. So now if the received data has got a lot of errors in it, then the amount of computation that you will need to do at the decoder will be vast. So again, I feel that this error correction technique is possible, but it is not one of the finest which is available in the literature today. Okay, now let's take a look at another error correction technique, which is called the trellis coded error correction, and this is assisted by CRC and bit stuffing. So to implement this, we refer to one of the papers called CRC assisted error correction in a trellis coded system with bit stuffing. This is a paper from the IEEE journal. It was published in the year 2010. So now this looks like a very novel error correction technique to me, and there is a lot of innovation that is done here. This looks like a very novel error correction technique to me, and then there is a little bit of innovation that is done here. I'll talk about it in a while. So again, it is seen that this error correction technique is really it's really good for some specific parameters in terms of modulation, in terms of the error channel that we are using, and in terms of the size of data packet that we are actually transmitting through it. So we'll take a look at the analysis and some of the simulation results. We actually designed the entire system in MATLAB, and to me, during the course of the entire project, I think that the decoded part of this exact receiver, this modified receiver technique which is mentioned here, was the most difficult part to be implemented, because it uses an all-new concept of using an extended trellis, which is a 2-dimensional trellis structure, and it also uses the concept of of a modified filter by decoding algorithm, which is different from what we typically use in the conventional trellis receivers and trellis encoders. So here is a block diagram of the transmitter. So again, we have the input data coming. Now, as the topic suggests, that here we have a CRC computation going on, and we are doing a trellis encoding along with bit stuffing. So we have all these 3 modules present in the transmitter, and now this is unlike a normal communication system where we just have one kind of encoding. So basically here we have a trellis encoding which is shielded with a CRC. So this gives a better performance, and we'll come to the results in a while, but let's take a look at how the transmitter is designed. So here we have the input data stream which is coming in, which is nothing but a stream of bits. Again, this input data goes to the CRC computation block. Now this would append some CRC bits to the input data, and then the entire packet is bit stuffed. So here in bit stuffing, what we are doing is, we are having, whenever we have a stream of 5 consecutive ones, we stuff a 0